Hello, I welcome you all in this sixth presentation on the subject joining technologies for the metals, and this presentation will be based on the principles of the fusion welding, and we will be starting with one welding process which is called gas welding. So, the different aspects related to the gas welding process will be talking about. So, basically the principles of fusion welding, that is what we have to talk. Now, the components to be joined after proper cleaning of the fitting surfaces using suitable heat source is applied in form of arc or gas flame, or like say the laser or electron beam, and likewise any other heat source. So, this will be directed onto the surface, so fitting surface of the component, primarily to bring them to the molten state, and so that the metallic continuity between the components to be joined is obtained after the solidification. So, the two things are important. The first is fusion and thereafter the solidification, which will result in the metallic continuity from one end to another. Now, if the fusion of only fitting surfaces is taking place, then the weld metal composition is considered to be almost the same as that of the base metal. So, in this case, when fusion of the only fitting surfaces is achieved for developing the weld joint, then the weld metal has same composition as the base metal, and in this situation whatever the partially melted grains are there of the base metal, on that solidification starts with their direct growth. No nucleation is needed. So, this is how the growth of the partially melted grains start without need of any nucleation. Now, depending upon the kind of the solidification conditions, here normally first the different kind of the grain structures are observed, and this kind of solidification where direct growth starts onto the partially melted grains is called epitaxial solidification. And this happens when the composition of the weld metal is similar to the base metal, but if the composition is different, then the nucleation and the growth mechanisms are involved for completing the solidification. Normally the columnar grain is normally 3 or 4 types of the grain structures are observed. One is the planar, which is very plain next to the fusion boundary. Then we normally observe cellular zone, then dendritic, and then equexed structure. So, normally the first is the planar, second is cells like this, third is in form of the dendrites, having the dendrites like this, and then equexed grain structure at the center of the weld. Likewise, the similar kind of structure is obtained from the other side. So, planar, cellular, dendritic and equexed grain structure is normally observed at the center. It is always preferred to have the equexed grain structure and therefore, to achieve this equiaxial gradient structure compositional modifications are carried out. But if the weld metal composition is different from the base metal, then the first nucleation on the fusion boundary takes place, thereafter the growth occurs. So, that is typical nucleation, and the growth modes are involved, steps are involved for completion of the solidification. Related with this only, since we have supplied heat to the for the heat for the fusion of the Fincke surfaces. So, due to the thermal conductivity of the base metal, some of the heat is transferred to the underlying metal below the fusion boundary, and this heat transferred to the base metal increases the temperature of the metal to the different degrees. Say here it may be 24 degree, then 100 degree, 500 degree, 1000 degree, likewise say 1200, say 1500 in case of the steels, or 1540 degree centigrade. So, as we approach towards the fusion boundary, the temperature keeps on increasing, and so the temperature the distance up to which temperature of the base metal is above the melting point, that is completely brought to the molten state, and thereafter sometimes if the metal is pure, then the boundary is clear, but if the metal system is an alloy, then we will have one solidus and one liquidus, and there is a temperature difference between the two. This wider is the solidus and liquidus, then there will be, so this corresponds to the liquidus, and then there will be a solidus line, and between these two we have the two phase zone where partial melting of the grains will be taking place, especially at the boundaries. So, this is called partial melting zone. This is found next to the fusion boundary, and thereafter this is a very much part of the heat affected zone, and thereafter all that distance up to which when the metal is heated by the heat supplied is affected, like say this is the fusion boundary, this is the partial melting zone. So, all that distance up to which the metal is subjected to the variation in structure and mechanical properties, all that zone is termed as heat affected zone. In the welding, the heat affected zone is one which is in an integral part of the fusion welding, and it cannot be eliminated. So, efforts are always made to control the size of the heat affected zone. Now, we will see the different metals responds to the heat in different ways, especially in the heat affected zone. Say this is the weld area, and now some of the metals like aluminum, this zone after the heat due to the heat of the welding, this usually get softened. So, the softening of the HAZ is observed, and sometimes it forms the very weak zone of the weld, and failure is localized, failure of the weld joint is localized in the heat affected zone. On the other hand, if it is steel, then the development of the weld zone, and thereafter narrow zone which is affected by the heat, it gets hardened in case of the hardening steels. So, this hardened zone becomes sensitive for cracking as well as the brittle fracture. So, in which way the heat affected zone will respond that depends upon the kind of metal system being welded, and this is not this heat affected zone cannot be eliminated because heat always gets transferred from the fusion boundary to the base metal due to the thermal conductivity. So, efforts are always made to reduce the size of this heat affected zone, because we do not have any control over the heat affected zone, only its size can be reduced. So, efforts are made in order to reduce the size of the heat affected zone. So, either the hardened zone in case of the hardenable steels, or the softened zone in case of the like precipitation hardenable aluminum alloys or work hardened aluminum alloys can be achieved. So, sometimes we have control over the weld metal in the sense that the weld metal composition can be adjusted as per requirement by using the suitable filler metal or suitable composition of the electrode in case of the consumable arc welding processes, but heat affected zone cannot be, we do not have any control over the heat affected zone in that sense, because whenever heat is applied it is formed only, therefore efforts are made in order to reduce the size of heat affected zone, so that adverse effects related with the fusion welding can be reduced. So, those processes where the amount of heat required for the fusion is more, size of the heat affected zone is also found to be more. This is what we have seen in case of the heat sources for the welding. Like I have told in the last previous lecture, I have told you that the gas welding, arc welding, and like say the radiation welding like laser, and all these are in increasing order of the power density, like say 10 to the power 7 to 10 to the power 8, 10 to the power 4 to 10 to the power 6, and like say 10 to the power 3 to 10 to the power 4 power density in terms of watt per centimeter square. So, higher is the power density, lesser will be the amount of heat that is to be supplied, and so that will limit the size of the weld zone, and that will also limit the heat affected zone width. So, if the heat affected zone width is reduced, that in turn will reduce the adverse effects related with the formation of the heat affected zone. Now, coming to the gas welding process and its principle. So, the gas welding basically uses one fuel gas, and usually oxygen is used for achieving the proper combustion. Most common fuel gas is like acetylene, thereafter propylene, propane, hydrogen, natural gas, or the other gases which can be used as a fuel gas for the gas welding purpose. However, the most commonly used gas is the acetylene, because it produces the highest temperature of the flame, while the temperature observed in case of the other gases, it may vary say 24 to 2900 degree, 2400 to 2900 degree centigrade, and this lower temperature adversely affects the process capability or the performance of the process, in the sense that it takes long first to start the welding, because it should reach to the flash point, or it takes really long to start the process and thereafter the welding. So, the other gases are not that effective in terms of the kind of the conditions which are produced by them during the welding. So, whenever normally like say we use one cylinder for the fuel gas and another is used for the oxygen, which is normally green, and this oxygen cylinder is normally coded like with the green color, and this is with the red color. There is a regulator with both cylinders. Regulators are used which will bring down the pressure of the oxygen or the acetylene to the normal working pressure, and then these are connected to the through the proper mixtures, and then it is fed to the torch. Now, torch will here this gas mixture will be coming out and here using suitable lighter or igniter, the gas flame is generated. So, the important thing is about the gas, the kind of the gas flame which is formed in case of the gas welding, because that affects the performance of the welding as well as its capabilities. The typical flame which is formed in the gas welding, it has, like, say, this is the inner cone and this is the outer cone. There are sometimes a third cone is also observed. So, this is called inner cone of the flame. It offers the highest temperature. However, amount of the heat generation in the inner cone is less. This is what we have, heat generation is less. This is what we have seen earlier in case of that how the chemical reactions are used for producing the flame, producing the heat using the fuel gases and the oxygen. And so, here heat generation is less, but since this zone is small in size and it is covered with the high temperature gases, so the peak temperature is temperature in this zone is high, and this can range like, say, 3300 degree centigrade in case of the oxyacetylene gas welding process, while the temperature of the outer flame is somewhat lower. It is 1260 to 75 degree centigrade. However, the amount of heat generation in the outer flame is much larger, but still, since the surface area of this flame is more and it is exposed to the atmospheric gases, atmospheric air. So, this because of these two regions, the temperature rise in this outer flame is limited, and if we try to plot the variation in temperature as a function of the distance from the flame tip towards the inner cone, then that is what we can see from this diagram, wherein, like, say, this is the x axis and y axis is showing the temperature of the flame. So, here say this is our outer flame and this is inner flame. So, now we can see how the temperature varies. Temperature at this end here, it is about, like, say, 1275 degree centigrade, and then on approaching towards this along the axis of the flame, this temperature will keep on increasing and then it will reach, thereafter it will start falling down. So, the temperature somewhere in the middle of the inner cone is found to be maximum, and therefore, and this is this side what we have, the torch this side we have torch tip. So, peak temperature occurs in the inner flame somewhere in middle of the inner cone, and the structure of, so therefore, efforts are always made in such a way that the distance of the nozzle from the workpiece is such that the surface of the workpiece is just at the peak temperature zone of the inner cone. So, this distance is used to decide where what will be the distance of the tip of the torch away from the workpiece. So, that it is adjusted in such a way that the inner cone is at the surface of the workpiece in order to increase its the melting capability. This is the purpose of showing this plot. Now, we will see with the change in the structure of the flame changes, and there are various features related with the flame of the gas, like this is the nozzle. Here we may have very sharp tipped inner cone and then outer one like this, or with, so this one is for oxidizing flame. There are three types of flame which are commonly observed, like a neutral, when oxygen and acetylene ratio is 1, and the 2 is oxidizing flame, when the oxygen is more than actually required for complete combustion. So, this ratio is generally more than 1 or 1.1, and when the ratio is reversed, like this ratio is less than 0.9 or less than 1, where acetylene is more than the oxygen, in that case we get third is carburizing flame. Carburizing flame is whenever it is developed, you will see that one additional cone corresponding to the region where incomplete, showing that the amount of the incompletely burned the gases are present. So, here we will see this is a very, so in this case the outer flame is narrow and short as compared to the neutral and neutral and carburizing flame. So, this is one thing, and this is very sharp and short. So, sometimes highest temperature is observed in case of the oxidizing flame. When the situation changes, like if we have higher percentage of the acetylene, in that case apart from the inner cone, one intermediate cone is also observed between the outer and the inner cones. Inner cone of course has the higher temperature, like say 3000 or 3100 degree centigrade in case of carburizing flame, and outer flame like say the 1250 or 60 degree centigrade. Third flame is corresponding to the suggesting the incomplete combustion. Incomplete combustion. If the gas is if the acetylene is marginally high, then the feather length is limited like this. If with the increasing percentage of the acetylene, the length of the intermediate feather increases. So, the length of the intermediate feather corresponds to the amount of the extra extra acetylene which is present, or the kind of, it suggests about the kind of excess in the percentage of acetylene with respect to the oxygen required for complete combustion. This incomplete combustion results in the carbon, lot of carbon which sometimes gets transferred to the pool. So, especially in case of the steels, cast irons, this the transfer of the unburned carbon to the weld, because in carburizing flame have lot of the unburned, incompletely burned fuel gases, and these gases get transferred to the these carbon incomplete burned gases producing carbon which gets transferred to the weld pool, and thus increased carbon percentage in the weld increases hardness and strength of the weld. Especially this is good for low carbon steels, but in case of the high carbon steels it may lead to the embrittlement and the cracking of the weld. So, this is what is about the different types of the flames which are formed in case of the gas welding. It is preferred to use the neutral flame where in complete combustion of the of the acetylene and the oxygen takes place during the welding. Sometimes when high resistance and high hardness is required, low carbon steels can be welded using the carburizing flame also. Now, depending upon the flame velocity depends upon the fuel and oxygen ratio and the pressure of gas mixture being used for the combustion purpose and the nozzle design, etc. And how effectively the combustion how effective complete combustion is taking place. These are the four factors that will govern the velocity of the flame. So, velocity of the flame when it is in the range of 10 to 15 meter per second, the flame is called quiet flame, or when it is in few hundreds of the meters, few hundreds of meter per second, like say 300, 400, 500 meter per second, it is called deflagration flame, and when it is greater than 1000 meter per second, the flame is called detonation. This kind of flame is used primarily for the spraying purpose or metal spraying purpose, where even the refractory and ceramic materials can also be used for developing the coatings. So, that is now in the case of the gas welding, since the protection is not very effective, so there is a possibility that the lot of gases in form of oxygen, nitrogen are present in the weld metal, and which will be producing the impurities in form of the oxides and nitrides. Therefore, to take care of these impurities, normally fluxes in form of paste, powder or solid coatings or liquid is applied over the fing surfaces before applying the heat, and this normally these fluxes, the borax is one of the commonly used fluxes. These have the elements like sodium, potassium, etc., to take care of to play an effective role in removing the impurities being formed. during the welding. So now, now I will conclude this presentation. In this presentation, I have talked about the fundamentals related to the fusion welding and how the gas welding, what are the basics of the gas welding with respect to the flame and how it can be used effectively. In the next presentation, I will talk about the different gas welding techniques and how do they affect the properties of the weld joint, apart from starting the arc welding related processes. Thank you for your attention.